For problem number 1, the formula to use is the formula for the potential around a point charge. Now in this case, the point charge that is creating the potential is the big charge Q. So the appropriate formula for that to consider is K times capital Q over R. So for the charge that is the charge Q, which is at position R, this formula would give its potential. Now for the charge that is at a position 2R, that particle would be at a potential kq over 2r. Note that the potential only depends on the position in space of the charge q. It doesn't depend on charge q. It's not a potential energy, it's the electric potential. So V prime here, which is the second charge, the 2q charge, has a 2 in the denominator. And since q is positive, V prime is less than V. So the one that is at the higher potential then, of course, is charge Q, which is answer A. For problem 2, the important formula to remember is the formula for the external work in the case of changes in electric potential. So that's Q delta V plus delta K. That's the fundamental formula. So the only thing that this depends on is the charge, the change in potential, and the change in kinetic energy. In this case, the particle is initially at rest and finally at rest also. So that tells us that the change in kinetic energy is 0. Now the change in potential here will be the final minus the initial. The final is minus 30, the initial is minus 40, so that change is plus 10 volts. And of course the charge is going to be plus E. So so that means that the external work is E times 10 volts, which is 10 electron volts. So the correct answer here is A, 10 electron volts. Another way to solve the problem is to realize, of course, that if you remember that the external work in this case, since if you remember that, since the change in kinetic energy is 0, the external work here is going to be proportional to the change in voltage, which is just 10. And since a proton has a charge of E, you know it's going to have a magnitude of 10 electron volts. And so that tells you it's either A or B. Now let's think about the sign of that work that has to be done. If you think about the direction of the electric field always points in the direction of decreasing voltage, and that is to the left. So the electric field here goes to the left, correct? Since it's a positive particle, if you just moved it from A to B directly, the force on that particle would be pointing in the direction of the electric field since it's a positive particle. So you would have to push on it in this direction, which is generally in the direction of its motion. So the work has to be positive, indicating that A is the correct answer. Okay, next problem, number 3. The fundamental relationship here that you need to remember is that the change in potential between 2 points in space is the negative of the inner product between the electric field and delta R, the change in the position between the 2 points. So in this case, we can imagine the equipotentials here equally spaced. And this formula here implies that if our delta R points in the direction of the increasing potential, so let's imagine delta R going this way, and we have increasing potential, that means that the electric field must point in the opposite direction. So if the electric field, note, points in the opposite direction, then the inner product between delta R and E will be negative, right? Because that angle between those two vectors is 180 degrees. So a negative inner product multiplied by a negative will give you a positive change in potential. So it's increasing in this direction. So the electric field must be pointing in the opposite direction. So in this case, the potential is increasing the plus x direction, indicating that the electric field must be going in the minus x direction. In question 4, we have 3-point charges that each have the same charge Q, and they're arranged on a ring of radius d, so the electric potential at the center. In this case, all you have to remember is that the electric potential of a series of charges is just the sum over all the charges and all the distances from the point in question. So in this case, since the point in question is at the center of the circle, the three distances are the same, the charges are all the same, so they all contribute the same quantity, which is kq over r. So the final answer, of course, is 3 kq over r, which is D. Problem 5 is an exercise in vector addition, and there are several ways to think about this, but let's just consider the possible directions that the forces that are exerted on particle P can be. So we have two other charges that we don't know the sign of these, whether they're the same sign of P or the opposite sign. But if you think about the directions that the force, let's say the force that this particle right here could exert, it's either going to be to the right or to the left. Those are the two possibilities. And they will have the same magnitude, right? Because it's just, if you flip the sign of this, it just changes the direction of the force, not the magnitude of the force. Now, what about this guy? Well, this guy is is perpendicular to him, so he's going to exert a force either away, if it happens to be the same sign as P, or down. So again, the forces this guy can exert will be up or down. Now, we don't know which case it is. We don't know if this force is to the left or the right, and this one is up and down. But we're going to add one of these forces, this one or this one, to one of these. So there are 4 possibilities, if you think about it, or several possibilities. You could add this one to this one, or this one to this one, or this one to this one, or this one to this one, right? There's 4. In each of those cases, though, you're adding 2 vectors which are perpendicular, and they all have the same magnitude, so you're going to get a vector which is this length, right? Which is like, the sum of the diagonal of the square. So it really doesn't matter what sign these are, as long as they have their directions of the forces are perpendicular. They always add to a vector of the same length. So that implies that the net force is the same in any of those cases. In problem 6, you have an electron that experiences a force directed along the vector which is in the direction of x plus 2y. In what direction is the electric field? Well, the fundamental relationship is that the force on a particle is equal to the charge on that particle times the electric field at the point where the particle is located. Since the charge on an electron is negative, it just implies that the force is in the opposite direction of the electric field. So the force lies along this vector, so the electric field must be in the opposite direction, which is just minus x minus 2y. So the answer is D. In problem 7, we have a problem very similar to what we've done in class. And the best way to do this is to compare these different charge distributions pairwise. So one thing which is obvious, and it's kind of obvious from the way I put the choice of the different situations, is that the charge distributions in A and B are opposite in sign. So the charge distribution in B is just -1 times the charge distribution in A. Now if you think about it, the force, the Coulomb force, of course, is proportional to the product of the two charges divided by the distance squared. Okay? So if you change, let me put a absolute value on this to make sure it's all positive. So you're just asked about comparing the magnitudes. So if you keep the magnitudes the same, but you just change the sign, summing up all those forces, you'll get the same. So A has to have the same magnitude as B, and also likewise C and D compare. They're just the negative of each other. So C must equal D. So all we really have to do is compare one of these to one of these. So let's compare C to A, for example. Now, some of this distribution is the same as this. For example, the first two, plus minus, is the same here, plus minus. Now these two will add up to give the same force in both cases A and C. Consider that P is a positive force, which is given. I'm sorry, a positive charge that's given here. Then this force will repel, this charge will pull it this way. This is a little closer than this one, so there will be a net force on P to the left. Likewise, that net force is going to point in the same direction in case C. So there's a little force to the left here, and there's the same little force over here. Now let's consider the effect of these two. These two cancel each other because this one pushes them this way, and this one right here pushes them that way. They're going to cancel because they're the same distance and same sign and magnitude. These, on the other hand, do not cancel. But let's see how they, in what relative direction they are relative to this one. Well, this is minus, so it will pull this particle this way. This is plus, it will push it that way. They both will add up to a vector pointing to the left, which is going to be coincidentally much bigger than this, although it doesn't matter because it's going to, since it's in the same direction, it's going to add to this, meaning that the net force on this guy is going to be bigger than this one. So C, this tells us that C is bigger than A, and that gives us the complete ordering then. So we have C equals D is bigger than A equals B, and that answer is C. Problem 8. In this case, this formula that is relevant here relates the electric field to the change in potential. The first thing that this formula implies that I'm going to consider is the direction of the electric field. Remember that this negative sign here implies that the electric field points in the direction of decreasing potential. So let's look at case B, for example. Here we see the potential is decreasing to the left, so the electric field points to the left there. And in case A here, we see that the potential is decreasing to the right, so the electric field must point to the right there. Let's look at some of these choices. Clearly, C violates that because it's got the electric field in case A pointing to the left, and we can also see that A violates that because it's got B pointing to the right. So now we just have to consider the magnitude. We've got, are the magnitudes the same? Are they different? Which one's larger? This formula also implies that as the spacing between the potential decreases, the electric field must increase because the product is the same. So here we have the electric potential surfaces closer together, so the magnitude of the electric field in case A must be greater, all right? We know that EA, that magnitude must be greater than EB, and there is only one case, the cases left that has that is D. The last two problems here are just some simple questions to think about concerning the motion of a charge in an electric field. The first one is pretty simple. We know that the force on a charged particle is equal to its charge times the electric field. That's the fundamental relationship which is applicable here. So a charge at rest, then in a uniform electric field, will experience a constant force because the charge is uniform in space. And since it's positive, it will be in the same direction. The force and the electric field will be in the same direction, so it will start moving, and since it's a constant force, of course it will move with constant acceleration. And the only answer here that has constant acceleration is B. In problem 10, this is really a example of conservation of energy. For the case of no external forces, the change in potential energy plus the change in kinetic energy should be 0. So since it is uniformly accelerating, it's speeding up. So we know that the potential energy must be decreasing. Another way I can write this, since I'm really just asking about potential energy, I don't really even have to separate it out here. It's kind of simpler to understand if I just write it like that. Again, kinetic energy, because it's accelerating, kinetic energy is increasing, potential energy has to be decreasing. It's just really just a application of conservation of energy. Problem 1 is a simple problem in kinematics. You have an electron released in a uniform electric field. So the relevant formula here is merely that the force is Q times electric field. Let's look at the magnitude first. The magnitude of the charge on the electron, of course, is E. And so we can write this out as 1.6 times 10 to the minus 19 coulombs times the electric field. This, of course, equals 8.0 times 10 to the minus 16 newtons. For the direction, let's see, the direction of the electric field is south, and this is an electron which is negative. So the force, by this equation right here, the force should be directed opposite the electric field, so the direction is north. To determine the acceleration of the electron, we just have to use Newton's second law, which of course tells us that the mass times the acceleration equals the net force, which is just the electric force in this case. To get the magnitude, we can write A equals F over M. Which equals the force from above over the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms, which yields 8.78 times 10 to the 14 meters per second squared. To two significant figures, I'll put that over here. 8.8 times 10 to the 14 meters per second squared. Now the direction, of course, is the same direction as the force, so that is north. Alright, for this last problem here, if the electron is initially traveling at 3.4 kilometers per second, how long does it take for the electron to come to rest? To solve this problem, I'm going to use graphical methods. I'll put time on the horizontal axis, and I'll mark the initial velocity here, call it v0. And of course he is slowing down. How do I know that? Let's just verify. Let me go back up to the beginning here. He's initially traveling south, and we know the force is north. So since the acceleration is north, so from kinematics we know if the acceleration is opposite the direction of the velocity, he is slowing down. So that means his speed will, and it's a constant acceleration, so it'll go down like this, and it will hit the axis here at a time t, which is in fact how long it takes for the electron to come to rest. Now we know the slope of this line is the acceleration, which we have from above. And graphically you can see that the magnitude of this slope, just the magnitude now, must be V0 over capital T. Now I'm not worrying about the sign here. The sign obviously of the slope is negative, but in order to solve this problem, all I really need is the positive, or the magnitude of the acceleration. So we can solve simply for t, and we get his initial velocity divided by the acceleration. I'll put in an extra sig fig here for the calculation. And that is 3.87 times 10 to the minus 12 seconds. So I'll put my final answer here as 3.9 picoseconds. For this problem, we are going to apply the fundamental rule for the potential of a point charge. So we have 3 point charges here, and remember that the potential at a certain point due to a point charge is given by this formula. So the net voltage, or the total voltage, will be the sum of the voltage from, or the potential from, contributed by each charge. Now the point in question is the center, and we see that the distance r is the same in all cases. And r, you can convince yourself, is going to be d times the square root of 2 over 2, because it's just half the diagonal of a square. And since all are the same, we simply get 3 times kq over d, the square root of 2 over 2, which gives me 6kq over d times the square root of 2. And if you don't like a square root in the denominator, you can multiply the top and the bottom by the square root of 2, and you'll get 3 times the square root of 2 kq over d. Now the next question here is, what is the magnitude and direction of the electric field at the center of the square? Now this question is a little easier than it may seem, because you can reason that the electric field created by this particle and this particle here, they both have the same magnitude at the center of the square, but they point in opposite directions. So the electric field from this guy and this guy cancel. So the only electric field that contributes is the electric field contributed by this one down in the lower left corner. Now the magnitude of that, we can see, is going to be kq over r squared. So let's take our r here and square that. And that is d squared 2 over 4, which is 2 kq over d squared. For the direction, that's easy because we are a square, and the particle that's contributing this electric field is in the lower left corner. The electric field will point to the upper right corner, towards upper right corner, 45 degrees to the horizontal. You can also, okay, in this problem we've got to determine the magnitude of the electric force on the lower left-hand particle. Let me draw this situation here because it's on the other page. So we're looking for the force on this particle right here. Okay, this is your vector addition problem. you've got to add the force due to this particle and the force due to this particle acting on that. I can draw those forces right here, so this can function as my free body diagram. And these forces, because all the charges are the same, the distances are the same, the magnitudes of each of these little forces here, E1 and E2, are the same. E1 equals E2, and it is equal to K Q squared over D squared. But of course, to add these as vectors, you need to add them head to tail, and we know that that is going to give me the diagonal of this square formed where the two vectors E1 and E2, whoops, I call that E1, let's call that E2. This guy right here is E2. And we can see that that is the diagonal of its own square, a square formed by these electric field vectors. So the sum, or the magnitude of the sum then, the E net, or the total electric field, will just be the magnitude of any one of them times the square root of 2, which is the square root of 2 KQ squared over D squared.